Again, welcome to Mathematical Structure for Computer Science, CS 113, also known as Discrete Mathematics. In these lectures, we're going to discuss about the nested quantifiers. So our main objective is to get the concept of nested quantifiers, also the order of quantifiers, translating from nested quantifiers into English. Also translating mathematical statement into statement involving nested quantifiers. Also translated English sentences into logical expressions, and then negating nested quantifiers. So again, in our previous lectures, we discussed about what is a quantifiers, and also we discussed about predicates and quantifiers in our previous lectures. So in this lecture, we're going to continue with the concept of quantifiers, but here we talk about a nested quantifiers. So we know, for example, in programming language, when we say a nested loop, it means a loop inside another loop. So it's kind of having a parenthesis. So we can see the example here. We have all x existing y, and then we have a parenthesis of s plus y equal to 0. So again, this is the basic concept of a nested quantifiers. So we said also a nested quantifiers are often necessary to express the meaning of sentences in English, as well as important concepts in computer science and mathematics. So example is given, every real number has an inverse, and it's the same as saying, here we are assuming x and y is our variables, and they are representing, or they consist of real numbers. So if I said x plus y equal to 0, it means any value of x, the inverse of that value will be the y value. So example 10 plus minus 10 is 0. So that's why here we are saying every real number has an inverse. So the inverse here make the addition of x plus y equal to 0. So let's say we pick 7. The inverse of 7 will be negative 7. So y is negative 7. So 7 plus negative 7 again will give us 0. Again, we discussed about these two symbols here, which means again, the upside down A means everything or all, and opposite E means existence of something, So here we are saying all x, the existence of y, x plus y equal to 0. And here we make sure that again, as we said earlier, the domains of x and y will be a real numbers, because here we say every real number has an inverse. We can also think of a nested propositional functions. So the concept of a nested, always you see a parenthesis. So example, we have the x plus y equal to 0 in the parenthesis again, all x existence of y can be viewed as, again, here we say all x, again we discuss about quantifiers. So all x, quantifiers of x, where quantifier of x is existence of y with the predicate of x and y. And here we say the predicate of x and y is x plus y equal to 0. So that's the concept again of a nested loops. So a nested loops again means we have a loop inside another loop. So in order to get into the inner loop, our outer loop have to have a true condition. So let's say to see if all x and y, predicate of x, y is true, we're going to look through the values of x. So here we are saying we have some values of x and also some values of y, and we said the p, x and y is true. So this means we have to go through the value of x, and at each step, we're going to look through the value for y. So it's like, again, nested concept. So I have two, here we have two variables, x and y. Anytime x is true, we can go into y, but if x is false, we can't go into y. And when y become true, when it becomes false, we come back to s again. So that's why we say the first step here, again, the concept of nested loop to see if the condition here with all x and all y, p, x and y is true. We're going to look through the values of x. And at each step, look through the value of y. So if I have x 10 and I have y 5, I will not go through the x from 1 to 10, then y from 1 to 5. No, I'll go through x 1, then I'll go to y from 1 to 5, then come back to s2, then y 1 to 5, s3, then y 1 to 5. So that's the whole concept here. And again, if you have taken the programming language, that's the same concept of nested loops. So at each step, loop through the value for y, which means if I have x and y, x, let's say, assume again, s is 5 numbers from 1 to 5. Y is also, let's say, 10 numbers, 1 to 10. I'll go through the first value of x. I'm not going to go through the second value of x, only the first value of x. Then I'll go through the y from y 1 to 10. When I finish y, then I'll come back to s2. Then I'll go through y, then I'll come back to s3. Then I'll go through all the y, then I'll come back to s4. So that's the first step. At each step, look through the value for y. And for some pair of x and y, if p of x and y is false, then we know that all x and all y p at s is false. So if it's true throughout to the end, then we say, okay, the condition here, p at s and y with all x and all y is true. But in the process, if anytime we become false, the loop will stop, terminate, then give us the false solution. So again, one more time here, the concept of nested loop here. Here we want to say if all x and all y, p and sy is true. The only way it can be true is when we loop through x from beginning and going through y. So if it's s is 5 times, I'll go through y s once, then go through y, or finish, then come s2. So I'll go through all the y 5 times. Anytime I'll go through the x. Now, if we go through all and we exhaust everything to the end and it's true, then it's true. But at any time we get false, we are not going to continue with the loop no more. So our condition will be false. So here, as we said earlier, at each step, we look through the values for y. What we mean by at each step is that at each value of x, if s is 1 to 5, when I start with s1, if the condition is true, I'll go through all the y5, all the y value, then I'll come back to s is 2, then go through all the y. So if y again is 10 values, every step or every time I'm moving in x value, I have to go through all the 10 values of y. So we said that if for some pair of s and y, and p of s and y is false, then we know the condition here is false. All x and all y, p at s and y is false. And both the outer and the inner loop will stop, terminate. So again, all x and all y, p, s, and y is true if the outer loop ends after stepping through all each s value. So you go through the first s value, that will give you the option to go. If it's true, then you go through all the y value. Then come back to second value of x, go through all the y value. Come to the third value. So you can see that the x, we don't go through all of them once. We take one, then if the condition is true, then we go to, because y becomes the inner loop now, or the inner condition. So the only time it will go through is when we go through all the steps of x. Now to see if all s and some y, p at s is true. So you can see the previous means all the s and all the y. That's why we have to go. Now, not all the y no more, but some of the y is true. Then we need to look through the value of x again. But at each step, we look through the value for y. Now, the inner loop ends when the pair s and y is found such that PSY is true. If no y is found such that P, S, and y is true, then the outer loop will terminate as all x and P has been shown to be false. Again, all s and existence of y, P, S, y is true if the outer loop ends after stepping through each x. Now, if the domain of the variables are infinity, then this process cannot actually be carried out. Infinity means, again, the condition will never be full, or we will never even end. So this is the order of quantifiers. Example given here. We let P, S, and Y be a statement that S plus Y equal to Y plus S. So here we are assuming that U is the real number, which means, again, all the values of S and Y, the universal value is real numbers. Then all X and all Y, PSY, and also all Y and all SPS have the same true value based on this condition, because if S is 4, Y is 5, it's the same as saying 5 plus 4 is the same as 4 plus 5. Now we say let QSY be the statement that S plus Y equal to 0. Here we are assuming that U again is a real number. Then all X and some Y, QSY is true, but some Y and all S, QSY will be false, because we know not all the Y. These are some of the questions on order of quantifiers. We have example 1, let U be the real numbers again. Now here we define PSY as S times Y equal to 0. So our condition said PSY is the variable S times Y equal to 0. Now what is the true value of the following? So they give us all X, all Y, P, X, Y. The answer here will be false. And the reason why it's false, we know that not all X and Y will meet this condition that S times Y equal to 0. Not all. We may get 0, of course. Let's say if S is 0 or Y is 0, it will be 0. But if we have 2 and Y is 3, S is 2, the answer cannot be 0. But this time, this will be correct, because we know every X and sum of Y, not all Y. So sum of the Y can be only 0. So any S value times 0 will give me 0. So this condition will be true. So that's why we have true. Now we also have some X and all Y. And also that will be true, because it's the same. At least we know S can have 0, Y can have 0. So if sum of some X, then I'll pick only 0 for X, then Y can be any value. The condition will be true. Now here also we have some X and some Y, and the condition have to be, the condition have to be true also. The last one, because again, X have 0, Y also have 0. So the condition have to be true. Now we have another condition here. Again, our U will be any real numbers. We have X divided by Y equal to 1. So this concept is almost the same as the previous one. What is the true value of the following? Whether it's false or true, all X, all Y, P, S, and Y, this will not be true, because sum, I can have 10 divided by 2 is 5, not 1. So here we say every X value and every Y value, when you divide S and Y, you get 1, and that's false. Here we're going to get true, because I can say, okay, any value of X, if I divide any value, if I divide any value of X, we are doing division here by 1, the answer will be the value. So this also cannot be true, it's false. Why is it false again? Any value of X, I will pick any value of Y. All means any value of X, but existence means it can be only 1, 0, or any value. But even if I pick 1 and I divide 7 by 1, the answer is 7. If I have X is 1 divided by 1, then the condition will be met. So the only true we're going to get will be the number 4, because I can have only 1 for x and y also 1. So 1 divided by 1. Or 10 for x, y also is 10. 10 divided by 10. If I'm dividing the same number, I will always get 1. So here we get false, all of them false, but the last one will be true. Because since, again, this means some values. So I'll pick the value I'll pick for s, I'll pick the same value for y, and the answer will be 1. But again, these conditions here, we can see everything is false. Why the first one is false again? Condition say s divided by y is 1. It can be any s value, I can pick 57. It can be any y value, I pick 3. 57 divided by 3 is not 1. So false. All value of x, some value of y. So I can pick any value of x and I divide with any value of y. I will not get true because I can pick 20 and y can be 1. 20 divided by 1 is 20. It can be 10, 2. The next one also we have some value of s but all y. So also is false. But here we say some s and some y. Yes, if I take 10, 10, I'll get 1. If I take 7, 7, I'll get 1. If I take 1, 1, I'll get 1. So only the last option is true. So these are some quantifications of 2 variables. So here we have our statement, and we're going to check when it's true and also when it's false. So let's see the first statement here. We say all x and all y, p, s, and y, or all y, or s, p, s, and y. And we say that p, s, and y is true for every pair x, y. For here we are using all s and y. Also, there's a pair x and y for which pair s and y is false, and that's again possible. Now all s and some y, p at s and y, true for every s, there's a y for which p s y is true. Also there's an s such that ps is false, as we saw our example. If I have s divided by y is 1, if s is 10 and y is 10, it's 1. But if s is 10 and y is 2, it's not 1. So some of the value will make it false and some will make it positive. Here also we say some x and all y, p at s. Here also we say the same thing. There's an x for which p at s is true for every y. Because here we have every y. Also for every x, there is a y for which p at s is also false. Now here we are doing some s, some y, p, s, y, or some y, some s, p, s, y. Here is some of both s and y, not all the values. So there's a pair sy for which pair sy is true. And there can be some pair sy is false for every pair sy. Now the next section, translating the nested quantifiers into English. So for example, we say we're going to translate the statement all x, c at x. We remember this is our, again, propositional logic we did. We have the conjunction and disjunction. So this is our disjunction. All this represent all. You can use the term disjunction or all. And this is conjunction or and. And I'm going to use all and and. So we have for all x, cs and c at x and some y, and c at y and f sy. Here we say the cs or c at s is s as a computer, and f x y is s and y are friends, and the domain for both s and y consists of all the students in your class. So if that's the case, we can say c at s as a computer, and here we say some y, because again y can be a student, and S and Y are friends here. So here we can say that, again, S is a student too. So we can say every student in your school has a computer or has a friend who has a computer. So we saw or here we can say that FS at this is friends, and the friends had a computer, and it's some friends. So we say every student in your school has a computer, which is all X, C at X, or some. The opposite EY means existence of some. So, and S and Y are friends. So that's why we say some friends have a computer or has a computer or has a friend who has a computer. Also, we can translate this. Again, when we are translating, this is what we call the nested quantifier. You can see that there's a sentence, there's a parenthesis, inner parenthesis, and outer. When we are translating, we have to consider the inner parenthesis very careful. So for example, if I know F is friend, yeah, I'm trying to say that we have a friend of X and Y. S and Y are persons, students. So S and Y are friends, and X and Z are friends, and Y is not Z. And then not, this is to negate. So not F, so Y and Z2 are not friends. So here we say there's a student, none of whose friends are also friends with each other. Because we can see SY are friends, but we have Z also, and or SZ are friends. But Y and Z are not friends. So another example here, we should translate the sum of two positive integers. It's always positive into a logical expression. So again, the sum of two positive integers is always positive. This time we need it in a logical expression. So here we can say that we can rewrite a statement to make them implied quantifiers and domain explicit. So here we say for every two integers, if these integers are both positive, then the sum of these integers is also positive. We introduce the variables S and Y and specify the domain to obtain. So we say for all positive integer S and Y, S plus Y is positive. Because they said that the sum of two positive integers is always positive. So we can say for all integer S and Y, S plus Y is positive. So the result will be for all X and all Y, if S is greater than 0, which means it's a positive value, and Y is greater than 0, again, S and Y, both values have to be positive. So that's why we are using N, which means the two condition. Then this tells me that if I had S plus Y, my answer will always be positive. Because if I had two positive values, my answer will be positive. And then use quantifiers to express the statement, there's a woman who has taken a flight on every airline in the world. So we have leg P, W, F. Here, W has taken F, which means the woman has taken the all flights or taken a flight. So we have a quantifier FA will be F is a flight on A. So the domain of W is all women, and the domain of F is all flights, and the domain of A is all airlines. And the question saying that use the quantifier to express that there's a woman who has taken a flight on every airline in the world. So there's some woman. So here we are using the existence of woman and all flights, because the woman has taken all flights, not all women, but some woman has taken all flights. Sorry, some woman has taken A is for airline. Sorry, A stand for airline. Let's make sure. Yeah, the domain of A is all airlines. So here we say that some women has taken some airline. Some woman take whole airline in some flights. So here we can see that there's a woman who has taken a flight on every airline. So the flights, not all flights. And here we say not all airline. So here we have some women has taken all flight or some flights in all airlines. Some flights is in all airlines. So we have the predicate of a woman flights and the flights of airline. So we also have the calculus in logic. This is an optional. For example, here they say use quantifiers to express the definition of the limit of a real value function f at s of a real variable s at a point A in its domain. So use the quantifier to express the definition of a limit of a real number function f at x of real value at a point A. So we have limit s approaches A f at s equal to L. So for every real number, there exists a real number such that f at s minus L should be less than our E whenever s minus A is greater than 0 or less than our sigma. And using quantifier, this is what we said. So the domain for the variables consists of all the positive real numbers, and the domain for S consists of all real numbers also. And this is another example. Choose obvious predicates and express in predicate logic. So example 1, brothers are simplest. So this means all X and all Y, B, S and Y is S, S and Y. B stands for the brothers, S is siblings. So here we are saying brothers are siblings. And here we say simply wood is symmetric. So we can say S, SY implies to Y and X, symmetric. With all S and all Y, simple of SY implies to simple of YX. Everybody loves somebody. So here we say all X, somebody, all S, and some Y. Love SY. There's someone who is loved by everyone. So there's someone who is loved by everyone. We get it opposite here now. So instead of all X, we get some existence of Y and all X. So there's someone who loves someone. So there's some existence of X and Y, love SY. Everyone loves himself. So for all X, love XX because you love yourself. So this is the concept of nested quantifier is the parentheses. Again, inner parentheses. Also, we can negate the nested quantifiers. So recall that the logical expression developed 3 slides back. We have the existence of W or A and existence of some F, P at WF, and Q at FA. We can use quantifiers to express the statement that there does not exist a woman who has taken a flight on every airline in the world. So this means we're going to negate it. This means some women have taken some flights in all airlines. So if it's opposite, then we negate it. Not some women. We have another example here. Can you switch the order of quantifiers? Yes, we can switch it. So for example, all S and all Y, PSY is same as all Y, all S, PSY. And yes, the left and the right side will always be the same. Again, because here, existence of all S and Y, so we can switch it, that's fine. Now, is this valid? We have all X and some Y, PSY, and then all Y, and no, some, no, so this will not be valid. So here we say no. The reason why, because again, we have all X and some Y, then we say some Y and all X. No, it won't be valid. The left and the right side may have different truth values for some propositional functions for P. So try S plus Y equal to 0. For PSY with universal being the real integers, the order in which the values of S and Y are picked does not matter. Now next, can you distribute quantifiers over a logical expression? Here we say yes, because the left and the right side will always have the same truth value. All X P at S implies to Q at S is the same as all S P at S implies to all S Q at S. And this is no. Because again, the left and right side may have different truth values. So pick S is a fish for P at S and X as a scale for Q at S, with the domain of discourse being all animals. Then the left side is false because there's some fish that do not have, again, that do not have scales. But the right side is true since not all animals are fish. So this will be the conclusion of our nested, again, our topic again, nested quantifiers. And again, wish you the best. Thank you.